In this module, we will discuss something that I promised to you a long time ago, what is called as quasi-statics. As the name suggests, this subject does not really qualify as statics, nor it qualifies as dynamics as we have studied. This subject lies somewhere in between statics and dynamics. The idea behind quasi-statics is that we assume all the sources to vary very slowly. They will certainly be varying with time, but we will assume that they are actually varying very slowly with time, so that the field patterns actually exhibit that same kind of time variation. So, the time rate of change must not be too rapid, otherwise we will have to use the full Maxwell's equation, and sometimes it is actually quite difficult to solve full Maxwell's equation. And in order to approach the solution at very high frequencies, one can actually take successive steps. Assume this quasi-static nature prevails, then make a correction to it, make a correction to the correction, and keep going until you are satisfied with the results that you are obtaining. That is the kind of approach that quasi-statics takes to subjects, and that is very powerful approach because it allows you to numerically do calculations and then keep making the corrections, okay, or you can analytically approach a problem which otherwise may not be approachable from Maxwell's equations at all. Let us consider one prototypical problem in which we will see how quasi-statics helps us understand more about the solution. This is not about completely a problem that we cannot solve. We can actually solve this problem using Maxwell's equation, but understanding that comes from quasi-statics perhaps deepens our understanding of Maxwell's equations itself. So, with that in mind, let me show you what problem that I am considering. I will assume that there is a large plate, okay, and one more large plate of conductors, okay. So, maybe this way I can hopefully convey to you that these are two quite large plates and they are separated by a distance h, okay. So, from center to center they are separated by a distance h. Please do not worry about the shape of the plate, as long as these plates, the conducting plates which we assume to be perfectly conducting, is quite large, then the shape by itself does not really matter. If you really want to be specific, you can always assume them to be two square plates, okay, or two circular plates. To these plates at the center we connect a certain voltage source, okay. So, this is my voltage source V of t, which is varying of course with respect to time, right. This is what I have, and in between let me put down a certain insulator which is described by epsilon, okay. This voltage source creates a certain charging current and begins to charge the capacitor, okay. Now, what physically happens when you connect such a source? What am I interested? I am actually interested in finding the electric and magnetic fields, okay. In the first cut or in the 0th order approximation, we will find the fields which are of 0th order, okay, which means that we will assume that the variation V of t with respect to time can be ignored, or we will assume equivalently that the variation will be the same as the variation for the electric and magnetic fields, okay. We will assume that this variation V of t is quite small. So, which means that we are assuming that frequency omega is quite small, okay. So, you may imagine that you take a voltage source of say 1 hertz or 2 hertz, and which is quite small, and then you take these plates which are quite large and then separate them with this one h, okay. And because this voltage and the current are varying very slowly, right, which of course will also depend on what is the capacitor characteristics as well. So, we will assume that the voltage source is varying very slowly, and also the charging current I of t is also varying very slowly, okay. So, the frequency is quite small, and the capacitance of the structure, we will come to that one slightly later, okay, allows us to write down the fields in its static form itself. So, you know, this is a situation where you would consider, if for example I have not taught you Maxwell's equations and you do not know anything about Maxwell's equation, then you will say, oh well, forget about the problem, let us simply assume a electric field which will not be varying with time, or it would be varying with time at the same phase as the voltage source V of t, okay. So, this is called as synchronous variation, and for the 0th order we will assume that all fields are synchronously varying, and because the variation is quite small with respect to time, the only fields that would be non-zero are the electric field E0 as well as the electric flux density d0. Okay. We will show why this is the case in few minutes, but we will assume that only these two quantities will be non-zero. Okay. That assumption we will justify very shortly. Physically what happens? Well, what happens is that once you connect the source, the current begins to flow and there would be charges around here, right. So, these charges which are being pulled into one end and pulled out from the other end will be in opposite polarities, but the charge cannot be situated right at the ends where the wires are connected. No, it has to the wire for this connection should come outside from the center and then join back here. Okay. So, this is how the connection should be made to the center, but obviously as the wire in the below is pulling out the charges, right, while the charges of opposite polarity are being pushed from the upper wire, these charges cannot remain near the nodes, right. They have to, because they are deposited on the same conductor and the conductor essentially is acting like an equipotential surface. Why is it acting like an equipotential surface? Because we have assumed that this is more or less a static scenario, right. So, the zeroth order is static scenario, everything is static, and in static case the plates will act like a equipotential surface. They would repel these charges and therefore, the charges actually get distributed, because any other charges that is remaining would start to repel. So, essentially what happens is, as you bring in the charges, these charges will spread all over the top plate. Similarly, the charges that are being pulled also come from a uniform distribution of the charges on the opposite polarity on the bottom plate. So, with the idea that charge distribution on the plates is all quite uniform, we can try to find out what would be the electric field. To find that one, we will not look at any other thing. What we will do is, we will try to write KVL kind of a equation, or we will go back to the definition of the electromotive force, which would be written in terms of integral of the electric field. Okay. Because the charge distribution is essentially uniform, you might imagine that the field lines would all be directed vertically downwards from the top to the bottom plate, and these field lines will be the ones which are the zeroth order fields. They would be varying with time, but that variation is synchronous, and this E0, which is down on this side, will induce a certain EMF in the path. What is the EMF equation? Well, if you were to integrate from the center to center, right. So, in fact, we should make some provision and say that the fields at the center at some distance. So, for example, if this is measured in terms of r, okay, this r equal to 0 corresponds to this point, and r equal to say a corresponds to the edge of the conductor plates. But we will assume that the fields are all uniform, we will neglect any fringing fields that would exist, which means that electric field E0 is function of both r and t, but this is it would be function of both r and t, but this is actually function only of t. Okay. So, because of that reason, I will drop the dependence on the radial distance r, but I will simply assume that this would be the same electric field, and that is justified because the plate areas are quite large and we are in the static region, the charge distribution is all uniform. Because of all this condition, the electric field to the zeroth order will be the same along. So, it is a uniform electric field. So, writing down the expression for KVL, okay, or writing down the simple definition for the EMF, we know that EMF is integral of E, right. So, over this particular closed path which begins, okay, so this is my closed path, okay, which is shown here in this blue line. Okay. Question: will there be any electric field configuration or any contribution to the EMF from these horizontal wires? There won't be any contribution because the wires are horizontal, they are conductors, but the electric fields are directed vertically down, and EMF measures the electric field along the loop. So, since there is no tangential electric field, there won't be any contribution from the top wire as well as from the bottom wire. Therefore, whatever the EMF drop that must occur across this structure must be exactly equal to V of t. So, in equation what we have is E0, which is the electric field which at the center is 0, and depending on time t, we might approximate this one simply as E0 t times h, because if you integrate a uniform electric field over the distance h, it would simply factor this h out, minus V of t that we have connected must be equal to 0. this allows us to write down what is E0 of t. E0 of t is simply V of t by h. So far there seems to be no surprise, but this will immediately allow us to write down what is D0. D0 of t will also be, and let us also put down the direction for the electric field. So let us say this is the direction along E. So where E is directed vertically downwards. Okay. Similarly, D0 of t will be also directed vertically downwards, and that is simply given by epsilon V of t by h. Okay. Now there is one other thing that we need to introduce. This other thing is the current that is associated with this particular loop, right. So what is the current that is associated with, or not with this loop, what is the current that is associated with the surface that we are going to consider? Assume that you have a nice surface which will just hug the top plate. Okay. If it just hugs the top plate, there are charges here, and this I of t represents the direction of the current that is coming in. Now, if the charges within this region are decaying, right, if the charges within this are decaying, then there must be a current out, and if you take the current out, that current out will be in this direction. So, the current out, okay, which must be equal to the charges that is decreasing dq by dt, this must precisely be equal to the current that is coming in, right. So, we assume the current coming in is given by I of t. So, this I of t must be exactly equal to the current that is coming in, right. So, because of this current continuity equation, the charge that is decreasing must be equal to the current that is out, but this current is equal to minus I of t, and cancelling the minus and minus signs, what we obtain is the current incoming onto the top region is actually given by dq of t by dt, right. But what is the charge that is enclosed? Charge enclosed is d by dt, okay, the d by dt actually comes out, but the charge enclosed is this d0 of t times whatever the surface area, right. So, if I call the surface area as say S, which would be the surface area. So, if you look at, and since d is also uniform, the charge that is enclosed will simply be d0 of t into S. The magnitude of d0 of t is epsilon V of t by h. So, we have d by dt of d0 of t s, which we can rewrite this as epsilon s by h dv by dt, dv of t by dt. What does this equation remind you of? If you take a capacitor, right, and then you charge the capacitor with a current I of t, wherein there is a voltage V of t across this, the capacitor current I of t is given by C dV by dt, correct. So, this variation dV by dt times C will be the current through the capacitor, and this equation is precisely telling you the same thing, except that the capacitance parameter C is given by epsilon s by h. Okay. So, this is clearly the capacitor equation, and that is what you will have, right. So, everything seems to check out here, and if we did not know any better, we would have simply stopped at this point and gone home happily, knowing that we have solved the capacitor problem. But unfortunately, we know little more than what we know, right. So, we know that this is not the end of the story. I need to know what is the magnetic field. What is the magnetic field here? Now, remember how the magnetic fields are generated. There is a current carrying conductor, okay, and around that there will be the magnetic field H. Now, what is the current that is being carried? Well, there is an insulator sitting in between, right. So, since the insulator is sitting in between, there is no option for us to have any current, conduction current through from one top to the bottom one. Therefore, for this 0th case, there will not be any magnetic field. Okay. So, the 0th order magnetic fields H0 as well as B0, the magnetic flux density, both must be equal to 0, because no conduction current. Okay. There is no conduction current. This completes our analysis of the 0th order, except that 0th order analysis is completely wrong. Why? Because we completely neglected one other type of current. We just said there is no conduction current and hence there is no magnetic field, but we know that it is not conduction current that exists in a capacitor, but it is displacement current, right. So, we know that it is actually displacement current that exists, and what is the displacement current? Del D by del T. Now, what should be the D that we need to use? Well, the only D that we know so far is D0. So, let us use this D0 of T as the source of the magnetic field. D0 we have already calculated, and using this displacement current we can calculate what is the magnetic field. What direction is this displacement current? It is actually coming down vertically, right. So, this is the top plate, this is the bottom plate, the displacement current is coming down in this way, this is the displacement current quantity. So, the magnetic field lines, because the current is coming down, must curl around, okay, in this nature. Okay. So, the magnetic fields must curl around, and they would be actually maximum near the center, and their density starts to decay, or the magnitude starts to decay as you go away from the center. Okay. So, if the magnetic field lines are all curling around and you take a particular curve which is at a radius r, okay, and calculate what is the magnetic field, you will find that because the field lines are all going in a say direction h, okay, and h is the azimuthal direction or the direction of the magnetic fields, and we assume that the displacement current through this loop is all uniform. It is a reasonable assumption because D0 is uniform, therefore, del D0 by del t is also uniform. Therefore, you pick a particular radius r, then the enclosed current will be given by del D0 of t by del t, that is the displacement current, okay, times the surface area of this particular loop, right. That must be equal to the current times this one, right. So, it would be equal to, so what is Ampere's law? Ampere's law states that integral of h dl must be equal to total current enclosed, right. So, total current enclosed is this fellow. So, h dl, integral over h dl will give you h along the direction h, right, 2 pi r is equal to del d0 t by del t s. So, the magnetic field component h will be given by along the direction h, okay, which is, you know, in the case here if you consider, that could be phi or anything, but this is a general direction that I am considering. What is del d0 of t? D0 we already know, it is epsilon v of t by h, therefore, the differentiation of that one will correspond to epsilon by h, okay, and you have the area here. So, no, epsilon by h into v of t. So, that would be dv of t by dt, there is s somewhere here because of the this one, and there is also 2 pi r, right. So, the magnetic field component h is given by h times, and we can actually rewrite this equation by writing down the expression here. What is the surface area S? Surface area S is pi r square, because this is the surface area of this loop which is at a radius r. Therefore, this would be pi r square. There is an r in the numerator, there is an r in the denominator, that would cancel, there is a pi and pi, that would cancel, and what I obtain is epsilon by 2h dv of t by dt times r. Okay. So, please take a look at this equation, convince yourself that now h, which is, you know, circulating the displacement current, actually vanishes. This fellow will be equal to 0 if v of t is equal to 0. Does it make sense? Absolutely yes. Why? If you take a voltage v of t is equal to 0, then there is, or if you assume that v of t is equal to 0 or constant, either for DC or for 0 voltage, which is again a constant voltage, there will not be any time variation. There is no way you can have the time varying fields inside the capacitor, which means that there is no displacement current, and hence the magnetic field will be equal to 0, right. So, the magnetic field will exist only when you have some time variation inside here. So, this magnetic field is also function of the radial distance, right. So, at r equal to 0, this fellow would be 0, but as r increases, the magnetic field would actually start to increase linearly. Okay. So, this is the magnetic field, but one of the things that we will have to look at now is that, is this the end of the story, is this the story that is ending, but unfortunately that is not, because now there is a time varying magnetic field, and you know that very well, if a time varying magnetic field exists, then it should induce an EMF, right. So, we will see what happens to that particular case. Okay. Again, go back to the top plate and the bottom plate condition. Okay. So, you have a top plate and the bottom plate. I know that I am going to consider a loop. I consider a loop from center to center, and this distance that I am considering will be say r, okay. This is say R or R1. So, at which point there is magnetic field. Now, how would the magnetic fields exist? The magnetic fields would all be curling around, right. So, they would all be curling around like this. So, clearly the magnetic fields around this loop, which is also time varying, must induce an EMF. According to Faraday's law, if you take an EMF around this path, there would be this EMF because of the changing magnetic field, right. So, we can actually find that one out, okay, by going back to expressions for magnetic flux density, and rate of change of magnetic flux density that is linking to this loop must give us the EMF. Okay. So, what would that be? First, let us write down the expression for H. H we have written down, we already know H of R is given by epsilon by 2 H dV by dt times R, which would also mean B, the magnetic flux density is also function of R, will be mu 0 epsilon by 2 H. This is, we are going to assume that the medium is all non-magnetic and is characterized by mu 0, right. So, this is mu 0 epsilon by 2 H dV by dt times R. Okay. So, for this loop what would be the, so if we were to integrate this loop along this particular direction, okay. So, let me integrate this loop in this direction, go from the top to bottom, sideways, and bottom to top, and again sideways. Okay. So, if I integrate this EMF around the rectangle, what I will get is very interesting.